Linked lists are fundamental data structures in computer science. They are used to store collections of data in a linear fashion. Each element, or node, in a linked list points to the next element. This creates a chain-like structure. Detecting cycles in linked lists is essential for maintaining the integrity and functionality of algorithms that rely on them. A cycle occurs when a node in the list points back to a previous node. This creates a loop. Loops can cause problems for algorithms that traverse linked lists. For example, a search algorithm might get stuck in an infinite loop if it encounters a cycle. Similarly, a traversal algorithm could end up visiting the same nodes repeatedly, leading to inefficient code. Therefore, being able to detect cycles is crucial for ensuring the correctness and efficiency of our programs. Cycles can occur due to errors in the implementation of algorithms that manipulate linked lists. For example, an algorithm that inserts a new node into a sorted linked list might accidentally create a cycle if it is not implemented correctly. Fortunately, there is a simple and elegant solution for detecting cycles in linked lists: the two-pointer method. This method uses two pointers, typically called slow and fast. The slow pointer moves one node at a time, while the fast pointer moves two nodes at a time. The beauty of this method lies in its ability to detect cycles regardless of the list's length. By moving at different speeds, the two pointers are guaranteed to meet if a cycle exists. This is because the fast pointer will eventually catch up to the slow pointer within the loop. The two pointers begin at the head of the linked list. In each iteration, the slow pointer advances one node, while the fast pointer advances two nodes. If there is a cycle in the linked list, the fast pointer will eventually lap the slow pointer. This means they will both point to the same node at the same time. When the two pointers meet, we know that a cycle exists. The meeting point itself might not be the start of the cycle, but it confirms the cycle's presence. At this point, we can take appropriate action such as logging an error, breaking out of a loop, or attempting to repair the list. No cycle detected. What happens then? If the fast pointer reaches the end of the linked list without ever meeting the slow pointer, we can conclude that there is no cycle. This is because if there were a cycle, the fast pointer would have eventually caught up to the slow pointer within the loop. When no cycle is detected, we can proceed with our algorithm knowing that the linked list is linear and free of loops. This ensures that our algorithms will execute correctly and efficiently. Removing a node from the end, a step-by-step guide. Removing the nth node from the end of a linked list is a common coding interview question that demonstrates a good understanding of linked list manipulation. Here's a step-by-step guide on how to do it. First, create a dummy node. Start by creating a dummy node that points to the head of the linked list. This dummy node simplifies the process of handling edge cases, such as when the list is empty or when we need to remove the head node. Next, initialize two pointers. Create two pointers, both initially pointing to the dummy node, then move the fast pointer n steps ahead. Move the fast pointer n steps ahead of the slow pointer. This is done to create a gap of n nodes between them. After that, iterate and adjust pointers. Iterate through the list, moving both pointers one step forward at a time. The gap of n nodes between them will remain constant. Now, update the slow pointer to remove the target node. When the fast pointer reaches the end of the list, the slow pointer will be n nodes behind it. This means the slow pointer is pointing to the node just before the target node, the nth node from the end. Update the slow pointer's next pointer to skip the target node, effectively removing it from the list. Finally, return the new head of the list. Return the next node after the dummy node. This is the new head of the linked list with the nth node from the end removed. Conclusion: mastering linked lists. Detecting cycles and removing nodes from the end are just two examples of the many operations that can be performed on linked lists. Understanding these concepts is crucial for any programmer working with linked lists. By mastering these techniques, you can write more robust and efficient code that utilizes the power of linked lists effectively.